Okay, well, we've been rushing through this, and I just want to take a minute to allay your worries about how quickly we're going, because you don't have to understand every part of this. I'm just trying to show that it wasn't a one-step process. It was a gradual building up of guessing at what might be, and then devising experiments that would either prove or disprove that theory. And that's science. You don't know what's always coming next. But you can make a great model of what you do know at the moment and test it. And so that's what we've been doing this whole time. Another important point is, I know this is a geology course. I haven't forgotten. But to understand geology, you can't just treat it as if it exists in a vacuum, because rocks are made of other things, and lots of other things, and they exist within the rules and realities of nature. And so, even though it's nice in school to chop up these subjects, chemistry, physics, biology, geology, geochemistry, however you want to chop them up, it's artificial. And in reality, these are all facets of nature, and they're just different categorizations of looking at nature. So you can't look at chemistry meaningfully if you don't know any physics, because in chemistry, materials and elements and molecules interact physically. They abide by the laws of physics. In biology, you can't look at cells without understanding chemistry and how chemicals interact physically. So these are all interrelated, and geology is just the same. We have to look at all sorts of different disciplines to understand geology in a really wholesome, full, meaningful way. So, having said that, I've set myself up to go on an even bigger diversion. Let's go back to Isaac Newton, 1666. He's discovered prisms and what they mean. A prism is a triangular, or it can be a number of shapes, but it's a piece of glass, usually triangular at its simplest, I suppose, that diffracts light. In other words, it splits up light, and it brings in daylight, splits it up into all the different colors: red, orange, yellow, green, blue, indigo, violet. And you can see that light is composed of these colors. Well, how did he know that light's composed of these colors? He took them, split them into the colors, went through other prisms, and made white light again. So it was very clever, and a really interesting thing to discover. 100 years later, Fresnel and Young, still studying light, proved that light is in fact a wave. It travels in waves, which is quite a big discovery. And when they go through that prism, how the wave travels dictates how it gets split up and how much it gets angled off, diffracted, when it travels through another medium, like a glass prism. 1864 comes around, another 100 years later. Maxwell proves that the visible light that we see, what we'd split up in a prism, say you just put a prism in the sun and it makes a rainbow on the wall, what you're seeing there is a splitting up of visible light, a very thin band on a much larger scale. And that scale is the electromagnetic spectrum. There's an absolutely excellent explanation of the electromagnetic spectrum in Jacob Bronowski's Ascent of Man, and I really encourage you watch that. But essentially, it's the idea that visible light is just one skinny little band on this larger spectrum of various energies and wavelengths. At the smallest and most high energy are gamma rays. Slightly bigger and lower energy, X-rays, then ultraviolet, then visible light, then infrared, which is just out of our visible range. Then microwaves and radio waves, which are very big wavelengths with not quite as much energy. It's all in one spectrum of electromagnetic energy. Einstein came along around the turn of the 20th century and sort of put this study into light on its head again. He found that waves are in fact, waves of light, in fact, act as particles as well, which is very strange. Why would a particle, like say you're shooting electrons out of the cathode ray, why should that also act as a wave and vice versa? So there's some pretty strange behavior to light, and it was an important thing to study. Now we know about the quantum interference and how particles of light, photons, and also electrons actually interfere with themselves as they try and pass through a double slit experiment. And I really encourage you to look up the double slit experiment and modified double slit experiment on YouTube, because it's hard to understand and it's beyond comprehension how such a thing actually exists. Anyway, where we need to go with this study into light is the spectroscope. And at the heart of a spectroscope is a prism. And what a spectroscope does is it takes a light source and splits up this visible light into distinct bands, just like a prism does, but perhaps more accurate. Depending on what the light source was, only certain wavelengths were present. So they might have one with a blue band and a violet band, and that would be one thing. Or if they looked at a candle, they might find a totally different pattern or spectrum of light. This was important because when they heated certain elements, they found that they could get repeatable patterns of spectra. So if they heated up a sample of copper in a hot flame and looked at the light it emitted, it was a really blue light. And looking at the spectroscope, they could see even more precisely that it wasn't just any old blue. It was a very precisely placed band of blue on the spectrum. And that just corresponds to a wavelength of light being emitted. So they did this with all sorts of elements, and they categorized all the elements they could based on the spectrums, or the spectrum of light that was emitted. And it was just like a fingerprint, so they could take any light source and figure out what was making the light, what was emitting the light. Now, if you think, that's pretty fantastic. It's sort of like measuring something from afar. And it really was, because they could look up at the sky, look at a star, look at our sun, and figure out what it's made of. So Bunsen and Kirchhoff tried doing their experiments, their categorization of the spectra of various elements, and they used everything they could make to give off light. And the most obvious light source of all, the sun, they actually had a problem with. First of all, because it's too bright to actually use one of their spectroscopes. Second of all, they came up, well, how they figured that out was they waited for an eclipse when the sun was dimmed and they could actually get some definition on their spectroscope. But they ran into a problem even once they had done that, in that there was a mystery element in the sun, a yellow band that didn't correspond to any known earthly element. And I mean, that was basically the end of the story. So there's a mystery band. Okay. It wasn't until about 1895 when I believe it was a chemist named Ramsay, Sir William Ramsay. I'm fuzzy on that. But he was playing with cleveite. That's a uranium mineral. And he was exposing it to acids and found that it produced a mystery gas. He didn't really know what it was. When they excited it, it gave and made it give off light. They passed it through the spectroscope And voila, there was this mystery yellow band that was only known to exist elsewhere on the sun. So of course they took the Greek god Helios and named this new element helium. And we now know that the sun is made of a lot of helium, among other things. That's pretty amazing that they could take the light of a celestial body and nothing else and determine what it's made of. It's just a fantastic achievement. Now Rutherford comes back to the rescue. He is experimenting with alpha particles. I think this is somewhere around 1910. And he was trapping alpha particles in a glass chamber, which is very difficult to do because you have to make the glass thin enough to let the alpha particle actually pass into it, which is very thin. And yet the container has to be robust enough that it can contain whatever's produced. So it was a very tricky game of glass blowing, and it took a lot of skill and labor to actually carry out the experiments. And so what Rutherford did was he passed alpha particles. He didn't know what they were, but he knew that they existed. He passed them, or put a radioactive source in front of his glass contraption, and so the alpha particles were emitted into this chamber and then bombarded with electrons. So it was a high voltage source of electrons that he bombarded the alpha particles with, which is quite an experiment. I mean, who knows what's going to happen? But what did happen was he produced a gas. Just as he was actually making an element from fundamental particles, which is quite incredible. And if you can guess, that element was helium. So from this, we know that alpha particles are like helium atoms without the electrons, because when we added the electrons to the alpha particles, it produced helium gas. So it just goes to reason that if you stripped the electrons away, you just have the nucleus of a helium atom, which is 2 protons and 2 neutrons. So the implications of this are pretty far-ranging, and we'll get into that. But what was going on here was basic particle physics. Now we do it with much higher energy, lots of electricity, high-velocity particles, and we're just splitting things apart and putting them together. And it's basically the same idea. So this was the beginning of particle physics. To get too much further into this is sort of difficult. A, because I'm not in any way qualified to talk about it, and B, because it's just fairly difficult and abstract to understand. You really need a background in math and theoretical physics, and even just normal physics before that.